So in this video, I'm not really going to edit it too much, but I wanted to discuss the patterns among prime numbers and non-prime numbers that I have discovered, because I just released this book and it basically covers about 3 years worth of research. So I've always been really good at math, and I wanted to basically figure out like what is the pattern among non-prime numbers and prime numbers, both of them. Because to me, the pattern among prime numbers and non-prime numbers is just as interesting. So like, one of the biggest questions I had was, why is there no pattern among odd composites when there's a pattern among even composites? And so I did find out at least one pattern. There are several patterns, I guess I could say. And when it comes to being a prime number, I did find out basically one specific detail, which maybe this will help somebody find an equation. But anyways, I released this book. It's called Antago bows, or Antago bows, however you want to pronounce it. And it's called A Pattern Among Odd Composites. This is on several platforms right now. I think it's on Apple and Amazon. I don't fucking care. But I do want to discuss a bunch of the... I come from like a video game development, programming background, and I wanted to create terms and I wanted to create concepts that weren't necessarily existing yet, because I find like there's so much stuff in math that we don't necessarily have terms for, and we don't really have structures for. And so by creating language for that, I thought it could really help us. One of the first things that I did was I looked through the prospect of, what would happen if, by dividing odds, even and odds, what if we had created a system that was trinary instead of binary? Because one thing that we know about odd and even numbers is that all evens are automatically not prime, correct? And so what would happen if we created a third category? And so I created a hypothetical third category that I call prog, which is just, it's literally just shorthand for progressive. In other words, a third category that's unnamed. So a progressive third category, we're just going to call it prog for short, because it's like a programmatic term for it. So we got odd, even, and prog for progressive. And so if we have like this progressive third column, we got odd, evens, and progs. What happens when we outline that and we look for the... Sorry, I'm trying to drink while I talk this. And we look for what is the pattern visually that we can decipher between evens and odds when we line them back to back, right? Because when you do it in like a binary chart, even, odds and evens, you automatically know that like the first column is going to have prime numbers in it, and non-prime numbers in it. But the second column for even would all be non-prime. So taking like a trinary look here, we've got, I divided it into two here. And one of the reasons I did that is because there's a lot of people have noticed that the first pattern that appears to sandwich prime numbers is like multiples of 6. And so I took a prog chart and I stuck it into a lineup of 6 here. And so we've got 1, 2, 3, 4, 5, 6. And if we do this, what we end up seeing here is that we have this entire column here that has prime numbers in it that are outlined in red. And then we've got here, all the prime numbers are outlined in red. So interestingly, in an odd, even, and prog setup where, it's 6, it's a 6-based column, you'll notice that all the progs and all the evens have no primes. And we'll just, ignore 2 and 3 here. So evens and progs all have no prime numbers. But all the odds do. So in a trinary construct for odd, even, and prog, instead of just odd and even, then all of the prime numbers are, in fact, very much isolated to the odd columns. So that's interesting enough. What do we get from that? I'm not entirely sure, but like this, I have a whole book here with tons of stuff. So let's keep going. So anyways, what I decided to do next was I created like this factor pyramid, and I just kind of built this in HTML and used PHP and stuff. So I created like this lineup here where you can do, let me see if I can find it. setup. And so what I did was I lined all the numbers, 0 through infinity from the vertical, and then 0 through infinity down the horizontal offsets, right? Well, I know that these are the verticals, but it's the horizontal offsets because these each represent a horizontal row. They each represent a row. And so we've got all the columns and the rows, but they both go from 0 to infinity. And by lining up the parts that are not prime or that are multiples, I started graying them out, and I started highlighting columns that were prime and all that jazz, right? Let me see if I can find that chart. Slant chart. I think it's the slant chart, actually. Yeah, here we go. So my slant chart, maybe I'll make these files available for you guys. So I really want people to find the ultimate equations. But I've got a ton of patterns here. Prime numbers are not random. They're not random, and I can tell you that. And I don't just mean that in terms of the multiples of numbers. I have a number of patterns in this video that is going to basically explain to you that prime numbers are not fucking random at all. What the equation is to ultimately solve for it, I don't know yet, but there's a ton of stuff in my book. I think that somebody could really find the equation. I truly do. So anyways, I've got this thing here, and what I did was I had all of these going on here, and if you have these multiples, grayed out, and I only grayed out, the factors or whatever for each multiple. So you got these factors for the multiples, and then you've got the columns that are prime numbers. Again, you'll see there's, you'll notice that there's this repetition of 6, right? So every time you get to 12, there's two prime numbers that sandwich it. You get to 18, which again is another multiple of 6. You've got prime numbers that are flanking that. And then you've got 24, you've got another prime number, and then this is an exception. So the blues are the exceptions. And then you've got the prime numbers flanking 30, which again is a multiple of 6, and blah, blah, blah. So all of that, 6 appears to be related to it, but what I ended up finding out is it's not that 6 is related to prime numbers. It's that 2 and 3 were more related to it. And there's a term for that I will go into further detail in this video with. But just to start, so if you take all of these factors and you gray them out, you end up with this series of noise, it looks like, where it's just kind of going out. But again, if you zoom out like I just did, right, then you end up with this interesting thing here where it appears like these are rays of sunshine. Do you see that? So these are rays of sunshine. So these aren't really random. So all of these factors aren't really random. They form these rays of sunshine, as you can see. And so all of these go back to the origin. So all of these here that look random, they're not random. They're actually just spaced out, basically, rays of sunshine. And what I call them is factor rays. I call them factor rays, or factor lines, whatever you prefer to know them as. But I call them factor rays because I wanted to start visualizing numbers as some type of ray of sunshine, and seeing if visualizing things in that way and some more kind of natural physical way was going to help find the answer. And so anyways, all of this noise where it appears like there's a bunch of random factors, these are just rays of sunshine basically, and they're just more spaced apart in various areas. And we'll get to the patterns more into this, but I just want you to understand what's happening here. So this is called the lumina. And the lumina here is this persistent ray of light that is the factors of multiples. And so going back to the book here, I went and I tried the odd, even, and prog thing with just instead of doing a 6 column visual. And again, the reason I was doing this is because initially I noticed that, again, it was these prime numbers were flanking multiples of 6 on the original Lumina chart, which is the factor pyramid. And so what I did was, I wanted to, back to this original thing here was, based off of my little factor pyramid, because these prime numbers were flanking numbers or multiples of 6, I did start off with a 6-column grid just to see what would happen with odd, even, and prog setup, where you have things divided by 3s. And so I did that. You can see I've got even have like odd, even, odd, prog, odd, even, prog, even, odd, prog. And the reason for that was to separate. I don't want to go into too much detail there. But I tried it as just like 3. And I thought, well, what if it was just divided by 3 instead of divided by 6? And so what you end up here is you have an odd, an even, and a prog column. And when you have an odd, an even, and a prog column, the evens have prime numbers in them. The odd columns have prime numbers in them. So, the interesting thing there is that the binary construct created this situation where the final column is where no prime numbers were in, right? It's an odd and even chart and an odd and even binary construct here. The even chart has no prime numbers in it. So that's the last column in the chart. And so if I did odd, even, and prog as just like a 3-column chart, then you'll notice that the only place where prime numbers fall is in the odd and even column. And the prog column has absolutely no prime numbers in it. So there's something going on there where, odds and evens and progs, there's something about setting up columns where one column happens to have nothing in it, and it seems to kind of be tied to how wide you make the columns. And so going back to this 6 wide chart here, the sextet chart, I have odd, even, prog, even, odd, and prog. The reason that these alternate is because if you look at the numbers, you've got 1, 2, 3, 4, 5, 6. But then look at the second row, right? 8. So like everything in this even column is an even number. Everything in this even column. So in a sextet chart, evens and progs are separated. So these are all multiples of 3. All the progs are multiples of 3. Do you see that? All of these are multiples of 3, and all of the multiples of evens, or of 2, is evens. And so in the sextet chart, it doesn't go odd, even, prog, odd, even, prog. It goes odd, even, prog, even, odd, prog. Does that make sense? So there's the reason why 6 appears to be related has nothing. I don't think it has anything to do with 6. I think it simply has to do with 2 and 3 being the first 2 numbers beyond number 1 and having multiples of them. So what first happens when you have numbers lined up is you start having multiples of 2s and 3s and things like that. And so things start to form this illusion. And so by creating like this odd, even, prog chart, you've got all the even numbers are lined up in the even charts, or column, and then you got all the odd numbers these are not multiples of 3, these are not multiples of 2, and that's where all the prime numbers are. So of course multiples of 2s and 3s are going to not be prime. So I think that the illusion of 6 having something to do with prime numbers, that's not to say that the 6 doesn't have anything to do with it, but I'm saying that I don't think it's that simple. I don't think that 6 is truly the key. It might have something to do with an equation later, but I don't think it's that 6. I don't think it's that surface level. I think that 6 just appears to have patterns with prime numbers flanking them, multiples of 6 having prime numbers flanking them, because 2 and 3 are just basically dancing rhythms throughout. They're the first 2 numbers, and so you have you can see it by creating this prog sextet chart, that the evens and the progs, these aren't prime. And they line up perfectly. So these are just multiples of 3 and multiples of 2. So I don't really think that that's the solution. I tried just doing the odd, even, and the progs. And again, you have like the prog column here. and everything is multiples of 3, but then the evens aren't perfectly multiples of even. So there's, how deeply do you want to go with that? It's almost arbitrary at this point. Like evens and odds is almost arbitrary. It appears to me that the only reason that evens and odds works is simply because all you're doing is creating a chart that is too wide. And of course, the second column is going to be everything that's divisible by 2. And so it's the same thing with prog. If you do 1, 2, 3, you create a 3-column chart of all numbers and just number them. The third column, everything's going to be divisible by 3. So prog is always not prime. And it's the same thing with evens. So odd and even is a binary construct. So evens are always divisible by 2. We just knew that. We know that because the columns are two. It's 2 columns wide. So the second column is always going to be divisible by 2. So that might be more arbitrary. This idea that evens are kind of, that's not to say that evens don't have, some base level relevance here, but I think a lot of people are wondering, like, why are all odds such and such, but all evens are not prime? And I don't think it's really that simple. I think that we as humans just created this simplified idea where, okay, what if we created a 2-column chart? But that's kind of arbitrary. And so by creating a 2-column chart of all numbers, everything in the second column is going to be automatically divisible by 2. And we have the same thing by creating a prog chart here, a trinary, a triadic prime chart. We've got like the third column is always going to be divisible by 3 because we just divided all the numbers by 3. So evens, odds and evens, odd, even, and prog, kind of like started getting me on this idea that, maybe odds and evens aren't necessarily so static of a division, and maybe it's more arbitrary. And so what I wanted to do is I wanted to start trying more things. So I went back to this sextet odd, or the sextet prime chart. And instead what I did was I got rid of all the even numbers and I did just a sextet odd chart. So what I have here is by getting rid of all the even numbers, you end up with an odd prog, odd prog, odd rhythm. And you can see that by the numbers because these are all just like, quote unquote odd numbers. And then the prog numbers, these are all divisible by 3. So all of the divisions by 3 end up in the center of each of these halves. So you've got odd, prog, odd, and of course prog. These are all multiples of 3. And so if you look at this, I ended up kind of highlighting numbers that were not prime, and some of these overlap, and so like it's hard to like have a cell that is two colors. I tried doing that and it didn't really look good, so I just kind of like left it as is just to illustrate. What you end up having is like numbers that are multiples of numbers start to form like these cascading lines. And so while that's interesting at first, it's not that interesting because you can see like with the blue here that they start to space apart further and further apart. And so there's not really a singular equation per se that's going to help you identify that. But, otherwise you would have like, this would be green, 77 would be green as well. 55 would be green, and so would 33. And so because they're all multiples of 11, so you have these cascading factor lines in any of the charts you create. Naturally, they just form naturally. And so, highlighting that again, you can see that they start to space further and further apart, whereas up here, the factor lines are kind of just like one next to each other in the corners. And so I don't really know exactly how useful that is to use the factor lines in trying to solve for prime numbers. So back to the other factor pyramid of the slant chart, I ended up having this realization that all of these quote unquote random gray factors aren't really random. They are in fact lines that can be accurately computed based upon the multiple, the factor, the factor and the multiple. So they keep appearing in periodic places. They're not actually jumbled together like they appear. They're just diagonal lines. going back to the origin. And you can see as I zoomed out here, I have an even bigger chart. You can just see the lines starting to form. And if you highlight them, you can see it forms this basically like infinite array of sunshine that just always, you know, goes back to the origin, but they're spaced further and further apart. You can even draw triangles to them. And so I don't really know what use that would have that might be useful in the future in solving for prime numbers. But they do form triangles, and you can start to compute, you know, various angles and things like that. But here's where things get really interesting, guys. So this is the part that you should like start to maybe listen up. Is I had studied this chart for quite a while, trying to find, I don't know, just some maybe some obvious pattern or solution, or not so obvious pattern or solution. And I had studied it for a long time. I think I took a year break off from it. I had studied it for months, and then I came back to it. Well, I started to notice something, and I took a break because I wasn't sure what to do with it. I came back to it like a year and a half later when I had like another burst of inspiration. And what I started to notice in the Lumina, the slant chart that I showed you, and by slant chart I mean the file name is called slant chart. This is just a factor pyramid, and so what this is referred to is the Lumina. All of the lines, these cascading lines, the factor arrays, this forms what I call the Lumina of all factors. And so what I noticed in the Lumina is that it's not just straight lines, as you could see here. So here you can see there's all these like rays of sunshine, the factor rays, which collectively create what I call the Lumina, which is an infinite, star of light going back to the origin. I started to notice this crazy pattern, guys. So I don't really know how useful it is, but it got me really, really fucking deep into numbers. And I think you guys should just like pay attention because I don't know. I don't know if there's something that can be gained from it, but there's certainly a lot about numbers that I had no idea was a thing until I really started to notice this. And so I studied it for so fucking long. I started to see this weird circle. I noticed these circles, they're arches. And so you can see here, I highlighted one of them. And then if you highlight the corners from that, again, all I'm doing now is just highlighting the factors that have been grayed out within the Lumina. I'm just highlighting actual factors inside of the Lumina. And then if you just follow this kind of like perfect arcing pattern and you only highlight the gray factors, it goes all the way back to the origin and it forms these perfect arcs. Do you see that? And you can do it with any of the numbers. Here I highlighted the connection so you can see it more clearly. And again, these were just factors. They weren't randomly there. I'm just highlighting the gray factors that are already there. They form natural arcs inside of the Lumina. And so you can do that for, so here I kind of broke down the numbers for the X and the Y values. So for the eighths, I call these Antago bows or Antago bows. And so what I did was I broke it down. And when you break them down, I refer to it as a SPArc. SPArc. So a SPArc is a sequenced palindromic arc or a parabolic curve connecting factor pairs to their amplitudes. I just wanted you guys to know the official definition that I had created for it. So a SPArc is an Antago bow. And the way that works is by mapping these values. So if you're just looking at the X and Y's of them, you've got 0 and 0. X value 0, Y value 0. This is one of the nodes on the arc. But then you also have 0 and 8, as you can see here. So 0, 0, 0, 8. And then the center is 16, X value 16, Y value 4. So right here, do you see that? This is the center of the arc. This is 16, 4. And what do we know about 4 and 16? Is this is the square root of 16. And then if you look through here, it just goes 1, 2, 3, 4, 5, 6, 7, 8. So this goes all the way up to 8. So it's 9 digits long, but it's the eighth SPArc. And it's a palindromic arc, which what I mean by that is, if you look at the x value, right? It goes 16, 15, 12, 7, 0. 16, 15, 12, 7, 0. And so we have these little arcs forming, which map out numbers that are completely palindromic. So for whatever reason, the lumina, all of the factors in the factor pyramid, when you create this lumina of them, create these perfect palindromic arcs. And it's not just with the number 8. You can do it for 7, and you can do it for 9. So you can see I traced out the 9th one, and I traced out the 7th one. And they're a little bit different for odds. So for odd numbers, there's 2 center digits. And then you've got 3 and 4. So you take 4 and you multiply it by 3, and you get 12. And this is a pronic number. 12 is a pronic number. Whereas 16 is a square number. And so all of the odd SPArcs, or Antago bows, Antago bows just refers to all of the SPArcs, collectively. So you got the lumina, and then you have the Antago bows. But then you have the individual SPArcs represent a single arc within the bows. And so you've got this kind of same thing here, but these are a little bit different. So it goes 12, 10, 6, 0, 12, 10, 6, 0. And then it goes up to 7. And so, and if you invert the y-axis, interestingly enough, you'll find that the x value is the product of the inverse times the y. So you've got 2 times 5. So 2 times 5 is 10. 6 times 1 is 6. 7 times 0 is 0. 4 times 3 is 12. So the inverse y, by inverting the y, I just inverted the y to see what that would do. And it came up with, I was able to come up with the equation for these bows, which is x equals y times n minus y. Where, n represents the index of the SPArc itself. So 8, you got the 8th and the 7th SPArc. So for the 7th SPArc, this is the index of the SPArc itself is 7, and you multiply that just using these equations here. So you'll go through the coordinates, and you'll come up with each of the coordinates for every point on the bow, on the SPArc. And so anyways, that was really interesting. And I thought, what if I could use that to help solve for prime numbers? I don't know. So I kind of kept going further, and I ended up doing something where I flipped the pyramid on its side, and I just kind of simplified it and color-coded it. And I decided to only do odd factors. So I have odd factors here, and I mapped them out. One thing that's kind of a little more abstract to understand is that only in an odd factor pyramid, and I'll have to remember why. You guys, I did so much fucking so many different pyramids. Let me try to remember why and how I came to this conclusion. Because I wrote it down, and it gets more confusing to me. Sometimes I read it because have you ever got really deep in a math problem, and then you move on to another math problem, and you're like, oh my God, what was I doing in that other math problem? So I'm trying to remember why I came to that conclusion. I wrote it down, but so let me try to get my mind back into how I came to this conclusion. Because there's a bunch of stuff in here that I was just following rabbit trails for several years. And I started to realize by following different concepts that the only thing I needed to do was look for the square roots within odd numbers in order to find out which odd numbers are not prime. And I came to this conclusion that you could only have, how do I word this without sounding confusing? So basically, let me pull this up. You only needed to have, let me see if you can understand this, because this makes sense to me. It makes sense to me. And this is how I came to the conclusion and started exploring this idea. So if you look at all odd numbers, no odd number is divisible by an even number, right? Because if it's divisible by an even number, then it means it's divisible by 2. So all odd numbers are divisible only by other odd numbers. And so I came to this realization that before a square number exists, they were all divisible by an odd number on or after its square. All odd numbers are divisible by some odd number. And so like they're only divisible by an odd number if it's on or after its square. And so for example, so for 3, if you multiply 3 by an odd number, you end up with the first, let's just say 3 times 3. You end up with 9. And so we have 9 here. And so we know that 9 is divisible by 3. And then you do 3 times 5 and you get 15. And then you do 3 times 7 and you'll get 21. And then you do 3 times 27. You do 3 times 9, you get 27. And so by taking odd number and finding all of its multiples by multiplying it by odd numbers, you wind up with this chart here where 3 times 3 is 9. 3 times 5 is 15. And so it forms like these cascading factor lines, as we saw, the Lumina before, which was like all numbers. And so it forms these lines. And you can do that with all of these. And what I came to the realization was that like I didn't really need to map out all of the factors on this pyramid. All I wanted to do was map out the lowest common denominator. And so by taking the lowest common denominator and only highlighting those, you can see the 3 is this orange, and you can see that 5 is this yellow, and you can see that 7 is this green, this like yellow green. 9 is this green. So you got 7 and 9, and they start to form these lines. If you just like get rid of all the other noise and you don't map out all the other factors, you end up with this kind of simplified chart. Like I don't need, so like for 15, I don't need to highlight 5. I don't need to. For 21, I don't need to highlight 7. I just need to highlight the smallest common denominator. And what I noticed was, and I explained it more in the book as to why that's true, they all trace back to their square. So all of the 3 go back to 9. It starts at 9 and then it goes outward. And the reason for that is the lowest common denominator that includes a particular number never appears until, so like it starts to overlap with other numbers at some point, but those numbers themselves also have factor arrays that like cascade from their own squares. And so it's okay. Like what I ended up coming to the conclusion with this pyramid was like it's okay to have multiple factors visible, but what I wanted to do was, why not only just map them out from their square, right? So like I didn't want to show 5 here because I thought that was just going to be unnecessary. Because if I reduce them all back and create like an index of its appearance on and after its square, you can get this chart here. Because everything before this is going to be divisible by smaller odd integer. So you got like 5 and 3 are only going to appear for 15, and 7 and 21 are, it's only going to appear with 7 and 3. I don't need the bigger number there because that's not necessarily going to give me a visual on this factor array that I was looking for. And so I just removed all the previous like smaller. You end up with like this sideways factor pyramid where you can see all of these. As you can see, they form these lines that go diagonal. And they all go back to their square. And so, by indexing them by their square, because that's the only thing that really matters, I started to notice these patterns. So if you look at 81 here, you've got this square here, and then you've got this square here, and then you've got this square here, and it starts to form this arc, right? Do you see my mouse? It starts to form this arc here. and it just goes back to the edge. And it's the same thing here. Midway through, it starts to form another arc. And it's the same thing here on 49. You can see it starts to form these arcs. And these were all common, like to every square number. So every square number, if you look at these, they form these arcs. So you've got, this is, there's like one digit. Do you see that? It goes like 1, 2, and then up 2, and then you have a highlighted square. Same thing here. Over 2, up 2, highlighted square. Over 2, up 2, highlighted square. Over 2, up 2, highlighted square. And it's the same thing with the next factor in the arc. So it goes over 2. It goes 1, 2, 1, 2, 3, 4, 5, 6. And then it goes 1, 2, 1, 2, 3, 4, 5, 6. 1, 2, 1, 2, 3, 4, 5, 6. And it's the same thing all through the entire pyramid. And so you have these perfect arcs that is, in fact, a pattern. These SPArcs or bows, that are also native to the original factor pyramid that I had showed you, the slant chart, it's part of this Lumina. They're also visible on the sideways odd square indexed chart or factor pyramid. And so this is a common theme throughout. And this, relates back to the fact that what I was telling you before is when you map out the arcs, the center amplitude is on even numbered SPArcs, it's always a square number. And it's the same thing with the odds. There's always this pronic number. And so, and what do we know about pronic numbers is they fall halfway through, right? They're like the midpoint between, a pronic number is a product of an even and an odd consecutive number. So they're kind of like, they're halfway points. They're not like exactly halfway points in terms of measurement, but they're halfway points in that you've got 5 times 5 is 25, 7 times 7 is 49, 6 times 6 is 36. But then if you multiply 5 times 6, you get 30. 30 is between 25 and 36. And then if you multiply 6 times 7, you've got 42, which is halfway between, well, not halfway, but it's the pronic midpoint between 49 and 36. And so pronic numbers are basically kind of like these midpoints. And so all of these arcs are aligned to square numbers and pronic values and stuff. It basically is the same thing, is that even on like this odd square index chart, they appear. So anyways, I had measured multiple things. I came up with a bunch of weird, interesting patterns too. I'll touch on these just real quick, but that's not the most important part about this. We'll talk more about the SPArcs, the bows in a second, because that's where a lot of the patterns really begin to emerge. But there was also some side patterns. So like the SPArcing or the SRFRIM factor pyramid is the square root factor index by multiples chart. So I only factored out factors and indexed them at their square. And you can completely do that. There's no reason not to, because of the way that just the way that the factors work for odd numbers. By doing this, I messed around with a bunch of different ideas. I came up with a thing called a sequin. You can actually sequence the index with its multiple, and you can find out these like other bizarre things about it. So for example, if you do sequence factors at their square, then you can extend them by their own value, and it will go out to form this pattern that I call a sequin. So, and it only, you'll find it by sequencing the square roots at their square. So you can see it starts at 9. So 3 gets factored out starting at 9, and 5 gets factored out starting at 25. So if we take 3 at its first index, which is 3 by 3, 3 times 3 equals 9, it'll start at 1, because again, we're only doing odd numbers on the chart. And so if we look at the odd numbers, if we take 3 and we just highlight 3 squares starting at its factor index, square root factor index, its SPArcing, the middle digit is the multiple. So this is the SPArcing is 1. This is which is index 0. So this is sequin 3, 0. because it's the factor 3. And then you multiply 3 times 3, which is the middle, and you get 9. But the other thing that's interesting is you can add these up, and this also equals 9. So 5 plus 3 plus 1 is 9. And so SPArcs will give you the sequins. And so the same thing with the second SPArcs index of 3. So the second SPArcs index would be 3 after 9, right? So the second index is, for 3 on the SPArcs pyramid, starts at the second column on row 15. You take 3 and you widen it by itself. And the middle digit is, and then the sum will equal 15. So 7 plus 5 is 12, plus 3 is 15. All of the odd numbers appear on even numbered SPArcs. So 8, the 8th SPArc is, its amplitude is, itself divided by 2 squared. And all the odd numbers appear only on even numbered SPArcs. Because if you look at, again, if we look at the 7th SPArc, all of the x values are even numbers. So every odd composite number is connected to a square on an even numbered SPArc. Okay, and we'll go deeper with this. We'll go much deeper. What is that? What is that relationship? So let's take 16 minus 15, and you get 1. And what do we know about 1? 1 is a square number. 1 times 1 equals 1. If we take 16 minus 7, it's 9. And what is 9? 9 is a square number. So we know, because of Antago bows, that every odd composite number is a square away from a square. Every one of them. Every odd composite number is a square away from a square. And I know this because I outlined more of them. And so we'll look at those. So here I just kind of outlined the SPArcs. These are the Antago bows. These are just all Antago bows. So each of these individual SPArcs, we've got the 8th SPArc again. If the first column here is 0 through 8, so this is the x value, correct? On that slant chart or whatever. Well, the y value on the slant chart. I just did it. I kind of inverted it so that you can see these here. And then this is the reverse of that. So you've got 0 through 8, 0 through 8 in reverse. And then this here is the alternating value, right? Because they're x and y's, they're coordinates. And so you've got the amplitude here, again, 16 and 4. And so if you look at 9, its amplitude is in fact a Penepronic number, which is 5 times 4, and then it cascades down, and you've got 20, 18, 14, 8, and 0. Same thing with 10. So we're back on an even SPArc. Its amplitude is 25. This is a square number, 5 times 5. And so if we take 25 minus 21, we've got 4. And what do we know about 4? 4 is a square number. And this just goes back to the equation, which is x equals y times n minus y. And so we've got 25 minus 9, right? 25 minus 9 is 16. And what do we know about 16? Again, 16 is a square number. And so we'll, on and on it goes. If we go to the 11th SPArc, again, the amplitude is in fact a Penepronic number, which is 30, 6 times 5. And that's just the midpoints, right? And then 12, 0 through 12. Look at the midpoint here, 36, which is a square number. So if we take 36 and we subtract 27, what's the difference? It's 9. That's a square number. So it's the same thing with 36 minus 11 is 25, which is a square number. So every odd composite number appears on a SPArc somewhere in the Antago bows. The Antago bows encompass every factor, just outlined as arcs. And so every odd composite number is on an even SPArc. And every odd composite number is a square value away from a square amplitude on an even SPArc. If an odd number is one number away from the even number SPArc, so let's say 7 is 1 away from 8 on the 8th SPArc, that does not count. And it's the same for all even-numbered SPArcs. Any odd number that is one number away from the index of the SPArc itself, this is not an indication of it being composite. I want you to keep this in mind throughout the video. Don't forget that, because we're only concerned with factors that are greater than 1. And so we can prove this, again, back to my chart here. Oh God, let's zoom it in. We can see here, all of these are a square number away from some square. And they form these arcs. So if you look at 81 here, it connects on an arc to 77, right? And what's 81 minus 77? 81 minus 77. 4. That's a square value. Same thing with 81 minus 65. You get 16. That is a square value. What we know then is that every odd composite number is a square value away from a square. In order for a number to be prime, it has to never, ever be a square difference from a square number. If you subtract it from a square number, from all square numbers, it can never form a square difference. If there is a square difference between an odd number and another square number, then it's not prime. And so that's one. Again, there's other stuff. We're going deeper. We know then that every odd composite is simply just an arc. It's on an arc. It's basically an inverted origin. So if you take the origin, right, and you separate it, I got these red lines here. So if you look at the origin, right, and you start tracking the odd numbers, imagine the even numbers are on the side here. I do have a version with that. I'm just not going to show it because I'm not worried about it. I think the people who are going to understand this video are the ones who are interested. So yeah, just imagine the even numbers are in here and they're also highlighted red. The rows are highlighted red. Then you would have this whole thing of cascading red lines, that are getting further and further apart from the origin, that are highlighting all of the square values, all the rows that represent a square number. In reverse, if you treat every square number like an origin and you highlight every square value from that origin in reverse, you wind up with every odd composite number. But they're different in the sense that every square number becomes its own inverse origin. And at the square intervals, you wind up with all the odd composites. So all of these odd composites are just square numbers in reverse from some square number that is representing an origin. So anyways, I'm going to go deeper here. So anyways, I decided to kind of map some of these arcs out in a visual pattern. And so I did like this vertical thing here where you can see the arc in like a vertical pattern. Let me see if I can pull that up. So I created like this JavaScript version where, let's see if we can just enlarge it. If you generate a grid in this kind of JavaScript thing here, you can click on these numbers and you can see the arcs that they compute, that they represent. Do you see these forming? And so they give this illusion of chaos, but there's no chaos here. They're just arcs. Jumbled together, they look chaotic, but they're not chaotic. So if you highlight all of them, you'll see that they form all the natural factors, the factor rays. You can see the factor rays starting to form. Do you see those? They just start cascading all the factor rays. So if I take all of these, let me just turn these all off again, and single this down, and just draw each one, you can kind of start to map them out and come to certain various mathematical conclusions. So like I started dissecting the arcs themselves and naming the different parts of them. And so I came up with a name for each of the different parts. So every y value we're going to refer to as a fulcrum. So this is a fulcrum. This is a fulcrum. This is a fulcrum. And this is a fulcrum on the 9th SPArc. A pan represents any two factors in a factor pair on a SPArc. So the lesser of the two pans is the aristopan, and the greater of the two pans is the dexapan. So if you look in here, we've got, this is the aristopan, and this is the dexapan. And so we have 1, which is the aristopan, and 8 is the dexapan. And if you multiply those together, you get 8. And so that is on, its y value is 8. So same thing here. If you take 2, the aristopan 2, and multiply by the dexapan 7, you get the 14th fulcrum, a fulcrum with a value of 14. And so I went and I named the different parts so I could just try to figure things out, right? By naming things, it just makes it easier for you to visualize in your head. So I just named stuff using different terms. So you've got the pivot, which is the midpoint between an aristopan and a dexapan. And I gave you the formula for that. The tonic is the highest point, which is it's a synonym for the amplitude, basically, of a SPArc or an Antago bow. The finial is the distance between a fulcrum and the tonic. So this here from 14 to 20 is a finial. And the midpoint here is the pivot. And then, of course, the tonic is 20, which is the pronic number of 4 times 5. So I named the different parts. The semi-beam is half of the length of the beam, and the beam is the distance between two pans. So 7 and 2, the aristopan 2 and the dexapan 7, if you subtract 2 from 7, you get the beam length. The length of the beam is 5, and the semi-beam, or half of a beam, the semi-beam is 5 divided by 2. And so I just named these things. A dial is just a rotated circle from there. So, I mean, they're just terms that they make sense. Moving forward, we'll take the arc here, and I went and I labeled each of the parts, and I just started like taking measurements, right? So we've got the entire height here, which is the tonic. So the tonic, which is the amplitude, is this midpoint here, this yellow line here. What we can surmise from this is that the fulcrum of this point here, this blue point, plus the finial, right? The distance between a fulcrum and the tonic. The fulcrum plus the finial equals the tonic. The length of the tonic. And we know that to always be true. And what do we know about tonics for even SPArcs? They're always a square number. So we know that there's some relationship between any given odd number, right? There's going to be some relationship between any of these, because odd numbers fall. So we've got 7 as a fulcrum. On the 8th SPArc, we have an odd fulcrum. Isn't that interesting? Isn't that interesting? So, because we have odd numbers, and they don't appear, because look, on number 9, they don't appear. See how they're all the fulcrums are even? So let's just go back to 8. All of the fulcrums are evens and odds. So every odd number can be represented as a fulcrum in relationship to this, the tonic, which is 16, a square number. So what we know then is that, and what did we find out before? What did we find out before? Guys, pay attention. This is really good. What did we find out before is that the tonic minus every odd number, which is a fulcrum. So we take 16 minus 7, it's a square number. So we know that the finial of the set of an odd fulcrum is always a square away from. We know that the yellow line A, which is the tonic, we know that's a square number. We know that B, the pink distance, the finial, we know that that is a square number. So check this out. We've got the fulcrum with a length of 21, and we have the finial with a length of 4, because it's always a square number away from the tonic. And so B is 2 squared, and A, because the tonic is always a squared number, is 25, which is 5 squared. So we have 2 squared and 5 squared. So what that means here is that the odd number, the odd composites, and every odd composite lies on some even-numbered spark, which means that 21 here relates to a Pythagorean theorem. The square root of B plus C equals A. The square root of A, obviously. And so what does that mean? Well, it's a right triangle. I don't know why and how this works and where it goes, you guys, entirely. Again, there's more stuff in this book I want to go over, and we'll go deeper into patterns and the prime numbers that I've discovered. But every odd composite number is related to the tonic or amplitude of some Antago bow, which, in this instance, an even numbered spark. So we can do a number of math equations to come up with what I refer to as the shadow factors. So these are the factumbrae. And so what that means is that there is a set of 2 integers that every odd composite number is related to. And so that would be, for 21, it would be 5 and 2. A here is 25, C is 21, and B is 4. So the square root of 25, the square root of 4 are the factumbrae of 21. But I just want to move forward here because this video is not about the book per se. It's more about the things that I found, and I want you guys to get into some of these findings, and maybe we can find some type of equation to solve for prime numbers, which is ultimately what we're looking for. That's what I want to find. So going through this, I did something that I call forward sparking. So sparking as a verb, what you do is you basically take that same kind of mathematical declination that I had showed before and how it descends on any of the sparks, right? Like on an even numbered spark. And so you can take an odd number and you can subtract 1 from it, and then you subtract 3 from that, and then you subtract 5, and then you subtract 7 from that. And you go down in this odd numbered sequence by, 1, 3, 5, 7. So 21 here, or 17 here, would then be 4 away from 21. So you're basically subtracting an odd sequence here, but ultimately what you're really doing is you're taking, so that odd sequence is related to square numbers, right? Because like 1 plus 3 is 4, and then 5 plus 1 plus 3 is 9, and then 7 plus 5 plus 3 plus 1 is the next square number, 16. So I just kind of want to fast forward here and find, so the most interesting thing is coming up. So basically then what you can do is you can take these SPArcs. What you can then do is you can break every piece of that up into a perfect circle. So you take the beam, which is the length between 2 pans, so the aristopan and the dexapan. And so like if you take the square here and here and here and here, you end up with a perfect half square at the end. And you can do that for every one of the SPArcs, and you wind up with this little visual. When we measure each of these lengths, so like we'll take the semi-beam here, which is A, and then E represents the fulcrum. You can see it represents some odd number. So ultimately what we're kind of concerned about here is an odd number prime or is it non-prime? So by taking all the odd numbers, which only appear on even SPArcs, we can measure that, represented by E. So this is an odd number fulcrum. So this is an odd composite number because all odd Y values on these SPArcs are composite numbers. They came from the Lumina. And so if we look at the semi-beam of the first concentric circle here, you add that to the beam here and to the beam here, and then there's a semi-beam of the bottom. What we can surmise from this is that all odd composite numbers are equal to all of the inner beams of the aristopans and the dexapans that fall between them at the base and its own fulcrum. So if we look at the fulcrum here this is the odd composite number Y value. The base has a semi-beam that represents a part of an odd composite number. All of the fulcra in between the base and the odd composite fulcrum we're looking at. And so we can come up with an equation for that. E, obviously, is the sum of A plus B plus C plus D. And so we can break this down, and we have 4 plus 6 plus 8 plus 10 halved and halved on the two endpoints equals 21. Because, again, we're just measuring the beam length. Because, again, these are perfect circles. So the beam between each of these, 6, 8, 10 at the base, and then 4 at itself, the fulcrum's own beam. We got 4 plus 6 plus 8 plus 10. And then we have the first beam, and we have the last beam, which represents this and this. So this is the radius, right? And so anyways, 4 plus 6 plus 8 plus 10 equals 21, but then you have these two. And so if you look interestingly here, what we have then is that all odd composite numbers follow this sort of pattern where it's it's a sequence of even numbers added to each other. So consecutive even numbers added to each other, but then you have the endpoints. If you take the semi-beam of the endpoints and add them together, what you will find is that their sum always equals the center of the two middle even numbers. So we have 6 plus 8 that we saw here, right? 4 plus 6 plus 8 plus 10. If we just remove the endpoints and add them together, what you will find is that their sum is always the middle digit between here, but it's an odd number. It's an odd number between the two even numbers, and it's consecutive. So you have 6 plus 7 plus 8. And this is true for all odd composite numbers, I found out. And so anyways, this right here is referred to as a harp and a crucibar. So this is the crucibar, and this is the harp that you derive from it, where you take the endpoints and add them together and just put their odd number in the center. The harps are very, very interesting. This is where things get partially, quite interesting with prime numbers. If we look into this sequence of harps that I had generated here, you can see that we have a list of odd composite numbers. And so we have 3, even though 3 is not technically composites. I'm suggesting perhaps it is composite. I don't know. I would maybe want to rethink that based on what I have found here. But we're not going to go too deep into that just yet. But one thing that I want you to see here is, so I went and I had mapped out all of the odd composite numbers and broke them all down into harp sequences. And so we have the number 3 here that again, we'll revisit this in a second. But notice how all of these odd numbers are all of the odd composite numbers. All of them. And every one of them can be represented as a consecutive even numbered sequence with an odd number in the center. A consecutive odd number in the center. So we have 2 plus 3 plus 4 equals 9. 4 plus 5 plus 6 equals 15. 0 plus 2 plus 3, there's the middle digit, the odd number, plus 4 plus 6 equals 15. 6 plus 7 plus 8 equals 21. 2, 4, 5, 6, 8. 8, 9, 10. 10, 11, 12. 4, 6, 7, 8, 10. And it goes on and on and on. We'll just scroll down further here. Even 169. 2, 4, 6, 8, 10, 12, 13. There's that odd number in the middle. It's still consecutive right in the middle. And then it goes 14, 16, 18, 20, 22, 24. That consecutive addition of even numbers. So 14, 16, 18, 20, 22, 24. Those are consecutive even numbers. And you can do this for every odd composite number. Every odd composite number can be represented as a harp. Now, one thing that I found interesting was if a harp begins with the number 0, you will have a second representation of the previous harp here. Notice how the center digit represents a factor pair, 3 times 5, right? Now, for whatever reason, harps can be represented as a specific factor pair. And when it comes to harps that begin with the number 0, you can get the twin factor pair. And so it's 5 digits long with 3 in the middle. 3 times 5 is 15. This is 3 digits in the arithmetic series of 15 here. So we've got 3 digits in this sequence with 5 in the middle. 3 times 5 is 15. And it works like this. So we've got 5 digits with the middle number 7. 5 times 7 is 35. Now, interestingly, like I had said, there are numbers that have harps that begin with the number 0. So you have, 0 and 2. These are 2 consecutive even numbers, 4 and 6, and then there's 3 in the middle. This is a twin factor pair. So 3 and 5 here. 3 times 5 is 15. And so anyways, the only time a number has a 0 at the beginning of one of its harp sequences is if that number is what I refer to as Penepronic, which means that it is almost pronic. And so what that means is that it is the product of 2 consecutive odd numbers. So 3 times 5 is 15. 1 times 3 equals 3. But 3 times 3 is not 2 consecutive odd numbers, and so 9 does not have a harp that begins with 0. And it's the same thing here. 3 times 7 are not 2 consecutive odd numbers, and so there is no harp that begins with the number 0 for 21. And it's the same thing with 35. 5 times 7, these are 2 consecutive odd numbers, is 35. And so there is a harp sequence, a twin harp sequence for 5 and 7 there. One beginning with 0. 35 is a Penepronic number. And it just goes on and on and on into infinity. Every odd composite number can be represented as a harp. Now, what I found to be interesting was that the number 3 came up as a harp sequence. Isn't that interesting? 3 is represented as a harp, but number 1 is not. And no other prime numbers are represented as a harp. So what we know then is that every even number can be divisible by 2, and every odd composite number is a harp. But interestingly, again, 3 is the smallest harp we could derive. So is 3 actually a prime number? Or not? I don't know, right? because the rules that we have established for what is prime and what is not prime is almost arbitrary. I know that there's like this rectangle number theory, but then I also know that number 1 has been retroactively redacted as being considered non-prime. But what we've never really been able to do is kind of separate which odd numbers are prime or non-prime. And what I've discovered is that there is two systems. There's two systems. Every even number is divisible by 2. Every odd composite number is a harp. And that includes 3. 3 is the smallest harp we can get from that. So perhaps because 2 and 3 are the base, the first numbers, the base numbers. So 1 is the first square number, 2 is the first pronic number, 3 is the first penepronic number. And so, maybe 2 and 3 are just base numbers for this arbitrary prime numbered system that we've created. And they should not be included as prime numbers. Because if we even go back to this chart here, the sextet prime chart, where evens and progs and odd numbers, and these would alternate into infinity, they have isolated all the prime numbers to this column. But then you have 2 and 3, these two exceptions. And that doesn't really fit, does it? It doesn't really fit. Perhaps 2 and 3 are not really prime, because 2 is divisible by 2, and 3 is a harp number. I think in the rectangular number world, I think that we want things to be so simple. There must be 2 rows, right? Which you can do with 2. You can do that with the number 2. So I don't know why 2 would not be considered, non-prime. Because we're creating these arbitrary rules. 3 is the first harp, the first penepronic number. 2 is the first pronic number. So where and what we get surmise from that, we know that there's something different about them. It would be okay for the number 1 to be considered non-prime, because you can have non-primes in these columns. But 2 and 3, when you divide the systems up, you have evens and harps. All odd composite numbers are a harp. All even numbers are simply non-prime, right? So all even numbers are composite, and all harps are composite odd numbers. Every odd composite is a harp. That includes 3. I don't know how far we want to go with that, but I am of the mindset that I think that we need to reconsider 3. Perhaps 3 is in fact not prime. It's just simply not prime, because this is the perfect system for finding every possible odd composite number. Harps, just break them down into harps. And 3 is what I refer to as penepronic. It's penepronic. So 2 is pronic, 3 is penepronic, 1 is square, 4 is the first, true, I guess, quote unquote, rectangle number. So I think we should rethink perhaps whether 3 is actually that. I don't know how deep I want to go with that. I don't think that that's necessarily relevant to this video, or to maybe an end equation. Maybe it is. But I do think that, most importantly here is we have two systems. We've got whether it's divisible by 2, so it folds in half, or if you do kind of this harp theme where you fold it, quote unquote, in half, but it's split by even numbers. And then you have this odd in the center there. So it forms kind of this hypothetical harp type shape in the way that the numbers are derived. And that includes 3. 3 is absolutely considered a harp number, even though it's not composite. Whereas every other harp sequence only represents an odd composite number. No prime number can be represented by a harp. If a harp sequence exists, it represents an odd composite number, with the exception of 3. And so you can quickly find every odd composite number in the entire universe by simply mapping out harps. You can just do it through harps. And that relates, again, back to where we derived this pattern using dials on the SPArc. By breaking these down into dials, you have like this kind of like seesaw balance of fulcra that are broken down into beams and semi-beams. And so you know then, based on these SPArcs, that every single odd composite number in the universe can be represented, this crucibar pattern, which, again, when you modify the endpoints and join them together, you get the Harps sequence. And so that Harps sequence, every odd composite number in the universe is represented by harp. You can quickly find every odd composite number by simply just mapping out harps. You don't have to go through this iterative nonsense of trying to multiply every possible odd number pattern. All you simply have to do is just find out every possible harp sequence that you could possibly conjure up, which is just any even numbered sequence. And then you have the two endpoints are just cut in half. And you can put them in the center there, like I said, for simplicity, which creates this harp sequence thing. And so anyways, yeah, so like we have the harp sequence. There is a harp sequence for the number 3. It certainly raises some questions about it. Now, of course, you know, harp sequences that begin with the number 0 cannot be necessarily represented by a crucibar. And so that changes some things a little bit there. But because the harp sequence does in fact map out every single possible odd composite number and skips over every prime number, we have a pattern here. There is a pattern among odd composites. And for whatever reason, 3 can be represented by one of the harp sequences. And so I find that to be very interesting. Moving forward here, yeah, so there is a number of pages in the back of this book where you can kind of chart out your own math and you can write your own notes. And there's a glossary. And so you can check out this glossary with that kind of describe a lot of the terms in the book. But yeah, I wanted to make this video and just kind of touch on a lot of my own discoveries on prime numbers, because I would really love for us to find a simple equation to solve for primality. You know, there's a number of concepts in this video that I think are really worth investigating, such as the fact that every odd composite number is a square away from a square. And so you can achieve that by SPArcing. I refer to it as the verb of SPArcing. You could SPArc through an odd composite number or through various, square numbers, and you can find the odd composites. So these aren't randomly just placed in here through these factor lines. They're also arcs all along here. And that's how all of these numbers are graphed out. A prime number simply falls between these. So yeah, these are a number of the fine discoveries that I found. There's a bunch more stuff in this book. I don't know if you have any ideas on how we could maybe come up with some sort of equation from some of these patterns, or anybody has the inspiration, you want to take a lot of these discoveries to the next level because you see more connections, by all means, please do so. Let me know. Link back to the video if you would. That'd be great. Let people know about the book. That's cool. Most importantly, let us know. Let us know your discoveries. Like, we need to find this equation. I don't know. I just believe that it's impossible. There's no way that there's no equation to solve for prime numbers. There's too many patterns that I have personally found and other people have found. And whether or not the things in this book and stuff have been discovered before, I don't know, because I don't know everything. But I wanted to go on my own journey and try to find an equation. And so that's what I did. I really hope you guys enjoyed and liked the content in the video. Please give the video a thumbs up, subscribe. I know this video is kind of thrown together, but we're on a mission here. We're trying to solve problems and try to find that equation.